Algebra 2, Common Core, Radian Angle Measure. So I'm going to read this little paragraph to you that just as distance can be measured in inches, feet, miles, or centimeters, rotations about a point can also be measured in many different ways. A common unit of angle measurement that is an alternative to degrees is called the radian. And you were first introduced to this in geometry last year. So a radian is another way of measuring an angle other than degrees. What we're showing here is a diagram of a circle, and it's rotating. You know, we know from our first unit of trigonometry that our angles start here and then kind of rotate here. We call this the initial side, the terminal side, and we've been talking about this angle in degrees. Like this angle looks to be about 60 degrees. And another way of measuring that, though, is by the length of the arc that it creates. Now, circles can be big or small, of course, but we can relate that arc relative to the length of its radius. And that's what a radian measure is. It's arc length in radius lengths. So like here, this is an example where they tried to show you one perfect radian. And what that means is that this arc length right here is equal in length to the radius. So that means that this angle is 1 radian. The arc that it opened is 1 radius length. And like I said, it comes to about I'm going to tell you exactly the angle measurement. It's pretty close to 60 degrees. I think it's in the 50s actually, but I'll tell you exactly what it is in a moment. But let me read this to you real quick. A circle is defined by a point in a radius. If we start with a circle of any radius and look at a sector of that circle with an arc length of equal to the radius length. So the arc length is equal to the radius length, then the central angle, will always be the same size. That no matter how big or small a circle is, if you were to cut a slice of the arc that's equal to the radius, it's going to be this shape. And so radian is just a way of measuring the angle in terms of how much arc it has relative to its radius. So no matter what, I can draw, a very sloppy angle here and say that, all right, well, this arc length is two of these like if this radius were 5, for example, and then I were to say this arc length is 10, that means that we could say that this angle in here, this angle theta, equals 2 radians. Because what that really means is it equals 2 radius lengths. I'm sorry, I'm writing pretty sloppy there. But the arc relative, so how many radius lengths is the, arc? And so you're not going to see radians that are like 500 radians or 100 radians and so on. So if you think about the circle here, how many, radius lengths fit around the circle? It's actually less than 7. So, a single radius length of arc is, a good amount of degrees. This shows you another perspective here that if we have a radius of 1 centimeter and the arc opens to 1 centimeter, that's a 1 radian angle, and we abbreviate it RAD. Well, what if our radius is 2 centimeters and our arc is 2? Well, it's still 1 radian. So you see that these two angles are congruent, that if we knew their degree measured, they'd be the same amount of degrees, like 57 degrees each. But we're calling them radians. But we could tell if these two angles are the same. And that was a big concept in geometry, was the concept of similarity. That things could be different size, but if the angles are congruent, then they're similar. And that's really what we're talking about here. And this angle is well, the radius is r units. Well, so whatever r is, if our arc length is also r units, then the angle is 1 radian. All these angles are congruent. So approximately how many degrees is a radian? Well, our calculator can tell us that by doing 180 divided by pi. And I'm going to explain to you in a minute why that works. It does come out to be about 57.2. We'll say approximately 57 degrees. So 180 divided by pi tells us how much this 1 radian arc is in degrees. So it's about 57 degrees. Now, why does 180 divided by pi give us that number? Well, this next picture right here does a great job of explaining it to you. So I'm going to zoom in real big to this picture here to show you what's going on. So all of these, sectors, except for this last piece here, all of these sectors are 1 radius length, meaning that the radius length is here. Well, this arc from here to here is that length, and then from there to there is that length, and from there to there is that length, and so on and so on. all the way around the circle. And we see that we get 6 radius lengths, right? Because that's 1, 2, 3 radius lengths, and then 4, 5, 6 radius lengths. And then there's a little something left over here. And this paragraph I'll go back to in a minute kind of explains that. But first, let me talk about the 180 thing. This is a radius, but what if I were to turn it into a diameter? All right, so I'm cutting the circle in half. How many radius lengths is half the circle? Now, half the circle, you know, is 180 degrees. How many radius lengths is that? Well, there's 1, 2, 3, and then a little more than 3. It's not quite a half. It's not even a quarter. It's a little less than that. Well, it's approximately, let's say, 0.14. And maybe kind of see what I'm saying here, that the half the circle, the 180 degrees of arc, is approximately 3.14 radius lengths. Exactly, it is pi radius lengths. 180 degrees of arc is pi radius lengths. So no matter how big or small your circle is, half of the arc is about 3.14 the length of your radius. And that's why I can then take, well, 180 degrees of arc divided by pi radians, or 3.1, divided by 3.14, tells me how many degrees about each of these 1 radians is, and that's where that 57 degrees came from. And then the full circle, well, the first circle is a little more than 6. It's about 6.2, and that comes out to be exactly 2 pi. Well, it makes sense if 180 is exactly pi, and then the other half is going to be another pi for a total of 2 pi. So this is a really important concept right here, that 180 degrees of arc is about 3.14 radius lengths. It is pi radius lengths, and the whole circle is 2 pi radius lengths. And that's really the key, though, is not even so much 360 equals 2 pi, but really try to remember that 180 equals pi. And I'm not saying these two numbers are equal. What I'm saying is 180 degrees equals pi radius lengths. Half your circle, and always remember that pi, it's about 3.14. A bunch of other numbers after that. It's irrational, but it's about a little over 3 radius lengths, 3.1 radius lengths. That's, whatever your radius is. So if our radius was 5, well, 5 pi, which is really, a little over, this is going to be somewhere around, 15 points, or maybe it's 16 points of it. I mean, let's find out exactly what it is. What is 5 times pi? It comes out to be 15.7. So if your radius was 5, your circumference, half of your circle, or your semicircle circumference, half your circle's circumference, the arc of half your circle would be 15.7, which is a little over 3 times your radius length. So it's important if you can make that connection, because a lot of the rest of the stuff you do with radians is going to make a lot more sense. So let's go to the next page. So with the conversion rule, we need to kind of know our special angles, the 90, 180, 270, 360, of course, the quadrantal angles they're called, but also the special angles like 30, 45, 60. It's very helpful to know what they are in radian lengths. So we know a couple already. The most important, we know that 180 degrees is pi radians. Well, I could just do some simple proportions here that, well, 90 degrees is half of that. Well, that would be pi over 2 radians. And again, what is pi divided by 2? So 3.14 divided by 2. But let's do exactly pi divided by 2. Pi divided by 2 is about 1.5, 1.6. And again, what that's saying is if you had, 90 degrees, here's a good example because the axes are drawn. This is 90 degrees. Well, that means that this amount of arc is about 1.5 that length. That's what we're saying by pi over 2. What else can we do here? Well, we could divide that by 2 also to get 45. And dividing pi over 2 by 2 gives us pi over 4. We know that 360 is double, so it's 2 pi. We saw that for a little over 6 radius lengths. The others would be 270 Well, 270 is 3 90s, right? 90, 180, 270. So I could take pi over 2 and multiply it by 3 to get 3 pi over 2. And those are your four quadrantals. Now I just need a couple of specials. How about 30? Well, it's a third of 90, right? So I can divide this by 3 to get 30. If I divide this by 3, I get pi over 6. Right? 'Cause dividing by 3 is times 1/3, tripling the bottom number. And 60, which is double that, 2 times this, throw 2 on top, simplify, I get pi over 3. So these are your special radians, degree things that you should, get to the point where you just, when you see pi over 2, you got to think 90 degrees. When you see pi over 6, you got to think 30 degrees. Pi over 3, 60 degrees. But the most important is that 180 pi. Now, what if I had an angle of, like I'm going to see down here, like 33 degrees? What is that in radians? Well, we do have a way of converting, ones that aren't super special. What you have to realize is that this is simply a ratio. And the ratio is that for every, pi radius lengths, for every 3.14 radius lengths, we're traveling 180 degrees. And so that means that if I want to convert degrees to radians, I just multiply by this. For example, going on to these questions here. If I want to convert degrees to radians, I just take that and I multiply it by pi over 180. And that's going to give me 45 pi over 180. And then I can simplify this. I could divide the top and bottom by 45 to get pi over 4. And that is what we said earlier for 45 degrees, is it's pi over 4 radians. 33 degrees, it's not going to be as nice, but times pi over 180 comes out to be 33 pi over 180, and then simplifying that, I'm sure I could divide them both by 3. I guess I don't need a calculator for that. Divide by 3, I'll get 11 pi over 60. And you can, you can't type in 33 pi over 180, but I could type in 33 over 180 and do math double enter, and we'll simplify that piece for me, but I got to remember that pi is attached to it. And then going the other way, converting radians to degrees, I can just flip-flop these arrows here to have the special ones, but the key is, going the other way is just multiplying by the reciprocal. So when I have a radian and I want degree, I have to remember, well, for every 180 degrees, I have pi radius lengths. So it's just the reciprocal. So if I want to convert negative pi over 3 into degrees, I'm going to multiply it by not pi over 180. That would give me pi squared. I don't want that. I want the pi gone. So I multiply by 180 over pi. And the pi's will cancel out here, and I'll end up with a negative sign still there. So it'll be negative 180 over 3, which is going to come out to be negative 60 degrees. Let's do this last one. 19 pi over 17 into degrees. So from radians to degrees. Multiply by 180 over the pi, so the pi's cancel out. And I'm going to have, 19 times 180 divided by 17. And I'm going to use my calculator for that math. So it'll be 19 times 180 divided by 17. Comes out to be, 201. And if I want to see if I can make this a fraction, not really. It's just going to be what 19 times 180 is. So 3420 over 17 is the final answer there. 3420 over 17. I mean, this is a tough one. If I gave you something simpler, it'd be a little bit easier. But that's the procedure. And really, like I said, the most important piece here is understanding that 180 degrees of arc is a little more than 3 of your radius lengths. And from that, we can get all these conversions, and going back and forth, we're just going to kind of multiply by these things here. All right, so that's kind of the stuff that you did learn last year in radians, but probably likely needed a refresher. Sorry for the long video. See ya.